Yeah, thank you very much. It's a great pleasure to be here for this conference for Rick. We are sort of now getting we are the old timers in conferences these days, and we end up, in conferences where many people in the audience, or most people in the audience, actually didn't know that we spent 6 years of our life at the same university, at the same place, between 1997 and 2003, and which, if you look back, were years where quite a few things happened on this two-dimensional conformal front. And in retrospect, it was like a very nice coincidence, a surprise. I think we both arrived exactly at the same time in Orsay. And in some sense, we both thought the other one was there before us or something. Rick was sharing, there was a division into different groups in Orsay. So he was in the geometry and topology group. I was in the probability and statistics group. He was sharing an office downstairs, from my perspective, with Jean-Marc Schlenker, who's around here. And I remember that we spent quite a few hours, discussing, but the discussion was like in the Rick style, which was like not talking much, looking at the blackboard, and I was just thinking, this guy knows tricks. I have no idea, where they come from. He had this, all this discrete, magic relation to conformal, discrete conformal stuff. This was completely new somehow in the story in all this world, seen from a probabilistic perspective. I mean, you have to realize that in those days, this conformal 2D random community basically didn't exist, right? It was just, a couple of offices in the world, people trying to think about how to make sense of these things. And during a while, basically, Rick's results were, the one, living proof of the fact that maybe something could be done, because there was this conjecture about the 5/4 exponent for the loop erased random walk that came out of outer space. So it was by such a Majumdar, but coming, from a mathematics perspective, was like no idea where it came from, and that was the first, actual result that was proved mathematically in that, realm. And then one day he said, oh, I have a visitor coming. How about we organize a hike or something in Fontainebleau? And then I saw there was this guy who was, obviously they were very close because they had been together PhD students with the same supervisor at the same place, the same age. And it was obvious that, it clicked, right? They didn't talk much, but they had a lot of respect and understood each other very well. I could see something going on, and that guy gave a talk about, I'm trying to use Loebner's equation to do something, and that was Oded giving his first talk on SLE that I heard. And also you have to understand that how important that was, that Oded came up with the idea of introducing the SLE or the tram, and he sort of thought, okay, what can I do with that? Well, there's one available thing, the mathematical front, is Rick's results about winding numbers in uniform spanning trees. And if you look at Oded's paper on scaling limit of, the SLE, first SLE paper, it was basically the whole part identifying SLE2 as the scaling, possible scaling limit, and SLE8 related to that was based on, Rick's winding number variances computations, and then that you could relate it to that. So that was really yeah. And then, of course, in some sense, we both, moved and had somehow several lives in some sense. So then he left to the US, and so it's sort of for us, I suspect, sometimes you look back and you say, oh, things pass so fast. That was just yesterday, but because there are like different moves, and okay, he went back to the US and so on, and I went to Zurich. So it actually feels quite long ago in some sense, but it's nice to be able to have some reminiscences of that. So I think I remember, well, okay, Beatrice and Cédric were there to witness that. They were his students and back then in Orsay, and I had Vincent Beffard and Julien Dubeda and others, and we were trying to make some joint working groups, trying to understand things we didn't understand to, some limited success, but sometimes it worked out. And I think my main contribution then was to try to convince, and successfully in 2 cases, which are in the audience, Adrien and Sanjay, that there was a great potential supervisor there at Brown University. Then they should not, be shy, and they should cross the Atlantic and take the opportunity to work with Rick. And I'm glad they, worked out well. Okay, so what else? Okay, I should talk maths now. One thing is, in some sense, if you come from the sort of probability, continuum probability French school, then Rick, what he introduced came really from outer space. And I always remember that we ended up doing some computations with SLE type based computation, and said, okay, now we get the exponents for these multiple arms in SLE2 and things like that. They come out and you can compute them, and you have to do some eigenvalue computations. It's prestigious. And then I went to knock at Rick's office and said, okay, so is that the same you get, And then he said, wait a minute. Well, obviously these non-intersection exponents have to be integers. And then, I thought, how? I looked at the formula. Yeah, okay, n squared minus n divided by 2 is an integer. That's true. But how did he know that? And so of course he had this other vision, more combinatorially based type thing. And I really, at that moment, I thought, gosh, this guy knows stuff I will never be able to have insight into. And it continued like that all over. On the other hand, maybe sometimes the continuous probability can surprise the other side as well. So that sort of, and I'll try today to tell you one story, a recent story about in that direction. However, I'll try to twist it in a way that relates it somehow to maybe some themes that Rick likes, holonomies and things about other results. I'll try to see how it goes. So I'll give a Blackboard talk. My Blackboard talks are actually not Blackboard talks, because if you look at the Blackboard at the end, there's nothing on the Blackboard either. So it's just it's a nothing talk. So the story I want to tell is, in some sense, focusing on some intermediate setup between the actual discrete world, lattice-based stuff, and the continuum world. And that's the world of cable graphs. So the idea is, you have a discrete lattice, and what I'm going to talk about will not be two-dimensional, so it's dimension independent. But it's maybe the most interesting parts all have to do with what happens in high, dimension 3 and higher. So you look at your favorite graph, and of course you could look at a lattice model and do like stats or many other things. You have like an Ising model on it, or the Gaussian free field on it, which say the Gaussian free field will be a random function that assigns to each vertex height. And so you have this random function from the sides on the left. Now, you could try to say, okay, as an intermediate between the discrete world and the continuum world, we look at the edges here as physical edges. Okay, and you look at, instead of the lattice, you look at the union of all these segments. So now that's a graph, and on that graph, in the discrete case, you had the random walk, and on that graph, you can define Brownian motion. So the Brownian motion on this type of thing will basically move around like Brownian motion here. And when it is at a site, essentially it chooses, to do excursions, attempts to, do excursion in any of the possible directions independently at random. So, it will be move like this. Then it will decide to go here, and then go here, come back here, etc. And if you sort of, look at the trace on the sides of this Brownian motion, you'd get exactly, in some sense, random walk with exponential waiting times. So somehow, in some sense, the trace on the sides of this Brownian motion is exactly random walk. Okay, so the very nice combinatorial continuous object that you can define on any cable graph is this thing that we like to call, so the Brownian loop soup. So that's the terminology we just came up with Greg Lawler in 2003 or something before, because I don't know why we had a Chinese soup or something before, but if you look in the context of 3 and higher dimensions, and you know the papers by Bridges, Friedrich Spencer, and semantic approach to quantum field theory type things, you won't say this is a loop gas. Well, that's the way the physicists would go about it. And so the idea is just to say that there is a natural measure on Brownian loops, or random walk loops, if you want to look at the trace of these Brownian loops in terms of random walks, which lives on any graph like that. And it's in essence, you look at the natural measure you can define on Brownian paths that start at a given point and end at the same point. Important thing is you don't prescribe the time length of your trajectory. It's just some sort of the natural measure you want to define on random trajectories that end up at the point where they start. And then there's a little trick, is that then you don't want to actually specify where the starting point actually is. So you get this cloud of loops. I mean, you get just the measure on loops, which are just trajectories. Parameterized by, you can view like a circle, and up to rotational reparametrization. So there's this natural measure on Brownian stuff, and again, this is in the discrete case. It's just this measure on loops is related to things when you do the exponent. You take the Laplacian, right, and exponential, you take a trace. So traces, you end up where you start, and taking the trace is the sum of all starting points. So this is very closely related to just, things having to do with the determinant of the Laplacian. And of course, you know that Rick's paper was called the asymptotic determinant of the Laplacian. So all this is, very closely actually related to these type of topics. So this is an infinite measure on loops. It's infinite because you have lots of very small ones sitting, puts an infinite mass on the small loops everywhere. If your graph has a finite Green's function, so if your Brownian motion is transient, then, locally you only have small ones floating around. And so then what you do is you take what probabilists call a Poisson point process. I think physicists would say grand canonical ensemble, right? Which we reinterpret probabilistically as a Poisson point process of something. And the idea is just say, you're using this loop to tell you how likely it is that loops pop up at random. And loops will pop up randomly, independently from each other on your graph, according to, using this likelihood given by that measure on Brownian loops. So this Brownian loop soup, there's one parameter that we usually call C, which is the constant multiple of this Brownian loop measure. The C is called C because we can refer it as retrospect what physicists call central charge in this two-dimensional world. And this, what I'm going to talk about is just one special case, which is C equal 1, or theta equals 1/2 for those who know the Legendre type parameterization, which is the particular version of the loop soup which is directly related to the Gaussian free field. So the picture is that you have this cloud, infinite, it's a random cloud of loops on your graph. They sort of fall down independently. And they're a bit, all over the place in your graph. Now, this cloud of loops has two very important combinatorial features. The first one is like the one I like to call rewiring lemma, which is in essence, and I'll try to make a picture which is a bit reminiscent of what Stas wrote yesterday. So I'm going to do, write the picture. It's sort of slightly misleading because it's very important for what I'm going to tell, that we're looking at this Brownian loop soup. But if you're in the discrete case, you can count, for each of the edges incoming in a given site, you look at all the union of all the loops that came. And for each of these edges, you look at how many times the loop went from here to there, joined these two went along these edges. And so what you see is, because life is what it is, the number of incoming edges, total number of incoming edges has to be even, because when you come in, you have to come out. And so you can look at the number of jumps along each of the edges of the union of all these individual loops. And then you say, OK, conditionally on that picture, how do these loops, how do these edges reconnect to each other in order to create the loops? And you can ask that question at every site. And the simple result, which is pretty elementary once you think about it, because you use c equal 1 over there, is that the way these things are reconnected into loops is just by doing a random pairing chosen uniformly independently at each of the sites. So that means that each of the sites, you choose, you can erase the picture of who's connected to whom, and you're just going to, decide that that's the picture. So you do this plumbing rewiring there independently at random. And of course, changing things might affect typically the number of loops, because you might put two loops together or split a loop into two. But the point is that this doesn't matter for that particular intensity of the loops. Okay, this is sort of the rewiring property. Yeah?
Are you implicitly using translation invariance?
No.
So this works even for finite graphs?
Yeah. This is sort of very general. Okay, if you, for what I'm going to say in a moment, for the relation of Gaussian free field, you might have to be a bit careful about, maybe it's easier to start with a case where everybody has the same number of incoming edges. Your degree is the same everywhere, but that's just, otherwise you can handle that as well. Yeah?
Sorry, I don't think you actually find this process. Like, what is the random sampling process of the loop space?
The random sampling process is this Poisson point process of Brownian loops. So the idea, you have some sort of a measure, which is an infinite measure. And in some sense, the way you should view it is that it measures, it's an infinite, it's a Brownian loop, so sort of it measures sort of the likelihood, the mass of a loop is sort of the likelihood of this loop appearing spontaneously. And then you just, let it rain for a while. Your loops are going to rain for time c. And you look at the union of all the loops that have appeared.
So you haven't told me what the measure of the loop is.
Well, it is basically, in the discrete case, is what I said, it is the natural simple measure on Brownian loops you want to define that I'm not going to write down. But if you're in the discrete world, which I guess you won't see, is basically any loop, if you're on z squared, any loop of length n will have a mass 4 to the minus n.
Okay.
That's it. One key thing is very important because, fermion bosons and all this stuff. For that setting, it's important to view these loops as non-oriented. So, these edges don't come with an arrow in this rewiring story. If you want to put the edges with an arrow, you are going to get c equal 2 there to have this rewiring property. And then this collection of loops, you see, there are a collection of oriented loops. And one way to explain Wilson's algorithm to simulate uniform spanning trees is to say that the collection of all the loops you erase during Wilson's algorithm is a Poisson point process of independent loops, basically, that you're doing there. It does not depend on the tree you're drawing. So what I'm just saying is that there's another version with oriented stuff that I'm not going to talk about yet. Yeah?
Yeah, going back to David's question a little bit, setting, when c equals 1, can you tell us what for a given edge, what the...
Yeah, you know everything, and maybe I'm going to explain you something which is, the next thing I have to be careful because I want to get where I want to get, which is pretty far ahead still. If you have your Brownian, and now it is basically where the continuum will start becoming very important, that you look at cable graph stuff rather than discrete world. Each Brownian motion is parameterized naturally by time. And therefore, it defines an occupation time measure. Each Brownian loop, if you think of each Brownian loop carrying a pack of sand which has a little hole in it, behind it, it will leave a sandpile that tells you how much time it spent, how it spread its time spent on the graph. So what you'll have is that you will see your graph like that, and one Brownian loop will give rise to, a random, sandpile that it leaves behind. Important feature about Brownian motion is that the set of points it has visited, except the ones that are at the edge of the support of its visited points, will have a positive, strictly positive sandpile. You can't go through a point quickly by speeding up and leaving no sand behind. So in some sense, the trace of the Brownian motion and the set of points where the sandpile is strictly positive up to the points that are actually on the boundary of the sandpile is the same. So now this story here tells you that it's very natural to look at the union of all the Brownian loops rather than the individual collection of Brownian loops, because you can recover the individual Brownian loops by just sampling independently at random, how to divide this into individual loops. The sandpile is measuring time, and the number of edges that you see on the edges is also time, so it's a natural thing to look at the cumulated sandpile created by all these Brownian loops that did pop up on your graph. So you have this thing called L of x, cable graph, which is the cumulated sandpile created by all these objects. Now the theorem, which in this form on the cable graph is due to Titus Lupu, but it's sort of an interpolation of the discrete version, which was actually recognized by Yves Lejean at some point, is that this thing is distributed exactly like the square of a Gaussian free field. So in particular, if you look at the trace on the sides, it's a discrete Gaussian free field. Square of a discrete Gaussian free field. Yeah, square. All right? So this is just telling you that you have this sort of, it tells you, okay, this cumulated sandpile here has something to do with, something is going on here. And of course, why is the Gaussian free field the basic building block in quantum field theory and so on, so on? Well, Gaussian free field has a Markovian property which tells you if I know the value of the Gaussian free field on the line, that separates your graph into two pieces, then the conditional distribution of what you see on the left and the conditional distribution of what you see on the right becomes independent conditionally on what happens at the middle. So that somehow the information doesn't jump, it just goes through the boundary of your wall, which is sort of a physical thing going on. The loop soup also has, because of the rewiring property, can also be seen to possess some sort of a Markov property. If you know the sandpile here and what happens on the left, what happens, then conditionally on what you see in the middle, what you see on the left and what you see on the right will sort of become conditionally independent. Okay, so this is sort of shows you that maybe something is going on here, and that's a good way to look at the Gaussian free field. Now, if you come from physics, so the important thing is that here, as opposed to when you're in the continuum world, in the completely continuum world, this Gaussian free field is a random function. It's a proper, nice random function, and the square is also a proper random function. The Gaussian free field is nothing else, when you look at it on the cable graph, as Brownian motion defined on these union of edges. And you just always have the constraint that each time you have a cycle, it has to be back at the origin because you have these different constraints. So it's just like Brownian motion on the universal cover, if you want, of your graph, but then you condition it to be actually, you project it on subspace where you actually can make sense on your thing of it. All right. So what was the next thing? Oh, yeah. So now I want to just make one comment, which is going to come back later. It's important. Suppose I have a point x here, a site x on my graph. And I look at the collection of loops that fall down on the Brownian loops. So I'm going to divide this into two sets of loops. One set of loop is going to be the ones that don't go through that point. Right? And another set of loop, which is independent because of the Poissonian nature of things, are the ones that go through this point here. Okay? And as a result, you could say that if I condition on the total local time of the sandpile at that point here, that sandpile at that point, the height is created only by the loops that go through that point. And so you end up with a decomposition by saying, okay, I take this total thing here or this total thing here. It can be decomposed into two parts, sum of two independent parts. The occupation time of all the loops that did not go visit that point. So that's just removing this point from this graph. So that's going to be a square of a Gaussian free field with zero boundary condition at that point. And then you add essentially the union of all the attempts of going away and coming back. So then you have a Poisson point process of excursions away from X. Right? And you look at the occupation time. And the fact that the sum of the occupation time of the purple and the blue ones is a Gaussian free field is just this thing which is known as Dinkin's isomorphism in the literature on these squared Gaussian fields type story. Now I can do just as a preparation of what's going to happen next. If I do 2 points, I have a red one, the purple one, and I have another orange one here. And I look at, now I can decompose it into three different ones, or 4 different ones. The loops that hit neither of them, they will give rise to a square of a Gaussian free field with zero boundary condition at these 2 points. Then the loops that only hit the red one, so these will correspond to excursions away from the red, not hitting the orange. The loops that hit only the orange ones, and then the loops that hit both. And of course, the loops that hit both will give rise to, they have to go from one to the other, and then they come back and come back. So they will give, rise to an even number of back and forth travels between these 2 points. So one remark is this identity is useful. It shows that all the correlation function in the Gaussian free field, I think, can be expressed in terms of connectivity properties for your sandpiles. Why is that? Because gamma is, it's just this random function, which is this generalization of Brownian motion that you define on your cable graph. So if I take this red point and this orange point here, you have 2 different things that can happen. Either the 2 points can be joined by a path along which lambda is strictly positive. Gamma is strictly positive. Or strictly negative. Right? They can be joined by a path along which neither L or gamma squared touches 0. So in that case, obviously, the sign of gamma at the 2 points has to be the same because it's a function, and if you go from one to the other without hitting 0, it means you're after the same sign. On the other hand, if they are not on the same island of excursion away from 0 of lambda or gamma, then so it's intuitively clear and can be made rigorous that you can choose the signs of these 2 excursions away from 0 by lambda independently, because Brownian reflection type principle. And therefore, you immediately see that the expected value of gamma x, gamma y for the Gaussian free field will be the same as the same thing where you just put an indicator function that x is connected to y. And by here, I mean x, there's a chain of Brownian loops. The first one visiting x, the last one visiting y, and they overlap. And therefore, they are creating a path along which the sandpile is going to be positive all the way from, have the same strictly positive all the way from x to y. Is that clear? So what you see here is that it is very important, then you sort of immediately see that this event here, which is this sandpile, the sandpile, there, x and y are in the same excursion away from 0 by this continuous sandpile, is sort of a relevant type of observable to look at. And using that, you can decondition, you can have the same, you condition on the value of gamma x squared and gamma y squared. And as Titus Lupu did, you can get explicit simple formulas for the probability that x is connected to y in that setting. And that's it.
Probably shouldn't ask because I've missed many other things. But how can I multiply by a 0, 1 indicator to have the same expectation after?
Well, because it has random signs.
Okay.
So when you're not here, basically you choose the signs independently and random, and therefore you get 0. Right. So now let me write down the statement, which in some sense, at first, when I bumped into it not so long ago, I felt, this is a type of statement, you see it, first reaction, you say, it's not true, can't be true. And then you realize, no, actually it's true, it's actually pretty easy to prove. And then you realize, how could we all collectively have been so stupid and not seen it before, because it was like looking at us, all these last 20 years, this thing was there and we didn't really understand it. Okay. So let me write you the statement. The statement is the following. I take a cable graph. I take my Poisson collection of loops that are introduced on this cable graph. I take 2 points. And I want to look at the distribution of gamma, or the whole distribution, the law of the picture. So you can choose the version you want in terms of sandpiles or square root of Gaussian free field of the picture, conditioned on x connected to y. Okay. So of course, in the previous description, you say, well, you have the loops that don't intersect, that intersect neither x nor y. You have the loops that hit x and not y. You have the loops that hit y, not x, and that. No, they're not in the same loop. They're the same cluster of loops.
Cluster of loops, okay.
And what I claim is that because of the fact that the sand left by each of the loop is strictly positive where it was, this is exactly the same. That's something you can read on the total sand pile by saying there's a path along which the sand pile is strictly positive between the two. Okay, so I was saying you have your 4 different type of loops that I described here. And they have to sort of conspire and interact in a certain way that they together create a path joining x and y. All right. And so the story is going to be, I'm going to complement it in a moment. And I'm just going to say this is a superposition of 4 things. So I'm going to draw, and the main thing is this one. They are independent here. So the same loops that don't touch x or y. essentially the same loops that touch x and not y. So these are this, when I say the same, is the same that you have in the unconditioned version. And now, a random odd number of independent excursions joining x and y. And so what I call an excursion here is a path that starts at x. It's a natural Brownian measure on paths that starts at x, doesn't come back to x, right? And you stop it at the first time it touches y, right? So it's like the part of a Brownian motion that goes from x to y between the last time it visits x until the first time it visits y. So here I cheated slightly in the statement because this random number in some sense is correlated to something that happens before. But what happens here is that it's very important that this number is odd. If it's odd, there's at least one. If there's at least one, then that one will create on its way from x to y this positive trace, this path along which the sandpile is strictly positive. So your first reaction should be, this cannot be true. He just told us that in this decomposition here, this number of excursion from x to y was even. And now he's just telling us, actually, it's equivalent to say that there's an odd number. The second, yes? Yes. So in some sense, the real statement is you also need to condition on the value of the squared of the height of the sandpile at both sides. And then basically you get, I mean, the Dinkin version was Poisson conditioned to be even, and now it's Poisson conditioned to be odd. And you sort of, it looks a bit strange. On the other hand, it's a very reminiscent of lots of things, with having, like what Stas said, and goes, some ideas of Eisenman and others, like, you put a sink and you put a source in the Ising model, and you have a switching lemma in the Ising model that, allows you to write things in different ways. And depending upon where you come from on the probability statistical physics version, you will, most people will find, it's a half an hour exercise, find your way to prove this once you know it's true, and I'm sure Dima will work it out in finite time. Important thing is, right, is that this only works because we're using this conditioning on the cable graph. This would not work if you try to do this, in some sort of discretized version. It's really essential that you are talking about this connection living on this cable graph. How does the proof work? Just an idea of the proof is, well, let's first try to show it's wrong. To show it's wrong, we're going to say, well, let's first see this Dinkin's isomorphism theorem, right? If I condition both points to be in the same cluster, you are sort of conditioning both points to have the same sign. And therefore, you could sort of, in view of the Gaussian free field, declare actually these 2 points are the same. And when you in terms of the law of the Gaussian free field, you declare they're actually the same, and you have excursions away from, you just declare these two to be the same, and then you have excursions away from that merge point, which would be, doing that, the one that corresponds to that, and the one that, do this on the other side. And in that perspective, you get exactly, the description I gave before, which is the law of the square, of the Gaussian free field when you condition on the value of that field. Is just the superposition of 1, 2, 3, 4, where 4 is a Poisson collection of excursion which is not conditioned. But then you put 1, 2, 3, 4 together, so it's not, it could be even or odd, but you put them together and you condition on the whole stuff together, creating a connection between x and y when they are not viewed as the same point anymore. That's option 1. Option 2 is take the decomposition I saw here, I gave you here, and says, well, I do the same, and now 4, because of what I explained before, can easily be shown to be exactly the same thing here, where you condition this to be even. All right? So what you end up by going all the way that direction is that this object where you take the union of these 4 instances, one with unconditioned number of excursions, and then you condition everything to be together to be connected, has the same law as the same thing where you condition where your number of excursions is even. But in both cases, these things interact in a complicated way because they are related by there exists a path joining x to y. But if the two are the same, give rise to the same thing, and the even thing is a subset of the unconditioned one, then the law of what's missing, the odd one, is also the same. Right? Because the one unconditioned one would be a mixture of even and odd. And if the result of the even is the same distribution as the result of the unconditioned one, then the one with odd number of inputs has the same distribution. But in the odd case, well, you don't have to condition at the end to check that they are connected because it's odd. You already have one path, and therefore you are connected. And therefore they're independent. So let me just make a little side remark, which is that for me, it was a bit like when you learn in probability theory and you like Brownian motion because you say, you could solve the Dirichlet problem using Brownian motion by starting a point at, I start Brownian motion from a point and I collect the value, the boundary value of the harmonic function, and that gives me the solution to the Dirichlet problem. And you always feel, that's not the way physics works. That's not the way, electric networks work. To compute the potential at a given point, you're not going to make the experiment of, launching infinitely many Brownian motion from there, and then they call you back and say, I arrived at the boundary. F at the boundary is that value, and then you take the mean value, and that's not the way electric networks work. The way it works is, say, there's a stationary process of excursions away from the boundary, and then you take the expected value in the center of how, the information each of these individual carry, and that defines you the object in the middle. If you go on Wikipedia page and you say, so this is like, for people who are not physicists, so excuse me, Philippe, you go Wikipedia page and you say, bosonic fields, are the thing that transmit forces that acts on fermions or things like that. You have this sort of statement that you say. And then you say, well, this exchangeability story that I said here, right, is, the Gaussian free fields is the bosonic free field. It's the sort of most elementary things of non-interacting stuff you can imagine. And this sort of picture that you have here has this, slight intuitive stimulation in the direction, okay, well, when two loops touch, then you don't know who is whom because you only look at the union of the loops, and they become indistinguishable, right? So these are like bosons, bosonic fields. And here what you see is that, okay, I have this cloud of loops. I say I condition x condition to y, connected to y. How does this happen? Well, actually the way it happens is x picks up the phone and says, I'm going to send you, an odd number of excursions from x to y, and otherwise the other loops don't feel anything, right? So the picture looks like, very much like, that the system creates sort of, these open-ended strings between these 2 points, and otherwise that don't interact with the rest. Okay, that's just a little side remark. Okay, so what I want to explain you is, different directions in which you can go from there, and what you can make out, what you could sort of do. And there are many, many options. I'll just quote just a few of them. The first remark is, if you are in the case where the Green's function between x and y is actually very, very small, this random odd number will be a Poisson random variable with that mean value given by the Green's function conditioned to be odd, and typically it will be 1. It's very difficult to have 1, so having 3 is even more difficult. So actually, typically, if these 2 points are very far away, the typical picture was that this random odd number will be 1. So in particular, you have 2 limits. One limit would be if you condition on x and y to be on the boundary of the same cluster. So this boundary of a cluster is this. You have your sandpile, and you're just sitting at the boundary of the sandpile where the height of the sandpile is 0. Okay, so you condition x and y to be on the boundaries of the same sandpile, then you get exactly 1 excursion from x to y, and nothing else goes. All these others will not go. This disappears. This disappears because you're not allowed to put any sand at x and y, and so you're just superposition of 1 and 4, which means that in that case, in that limiting case, you have a loop soup with no loops allowed to go through x and y, and just 1 excursion between x and y. If you go in the limit, the continuum limit, when you let the mesh of the lattice go to 0 in your dimension 2 or 3, that's what's going to happen. The Green's function goes to 0, and you'll have the same feature that the picture will be, these loops that go through x and these loops that go to y will disappear. They are typically not there. And so then you'll have the picture of the whole story where x is conditioned to be connected to y in the continuum is the same as an unconditioned loop soup plus 1 excursion from x to y. All right. And so if you look at in the 2-dimensional case where you have this conformally invariant stuff, there are tools to attack that directly. And if you look in one of the recent papers by Antoine Gégaud, Titus Lupu, and Wei Qian, they have that statement hidden somewhere in the 2-dimensional case. But what I tell you here, that's a much more general story. So that's one direction in which you can go. So which other direction do I want to mention now? Another important direction is you fix x and you let y go to infinity in Z3, say, or ZD, NED greater than 3. In that case, it's exactly the same story. You get an unconditioned loop soup plus 1 Brownian excursion going from x to infinity. So for people in the statistical physics community, usually when you try to define this thing, look at the law of a percolation thing where you condition x to be in an infinite cluster. That's known as the incipient infinite cluster measure. And that's usually a very complicated structure because you are conditioning, this object. Showing existence is complicated. And there's a sequence of papers with, on 2 groups of people, Jian Ding and collaborators and important collaborators, and a group of people with Pierre-François Rodriguez and Alexis Prévost and Alex Drewitz, who have been building up basically several hundred pages where you end up with the outcome that you can construct the incipient infinite cluster measure when in ZD for that picture. Here you get it for free. The law of the incipient infinite measure in that thing is just an unconditioned picture plus 1 Brownian excursion going from x from 0 to infinity. Right? So it comes as a surprise that you have an explicit description of that object here. So it's another symptom of the fact that there are some miraculous combinatorial features. Now the point I want to emphasize now, because it's Rick's birthday, is something that goes in the direction, a variant of this result that goes more in the direction maybe of things Rick has initiated, and I mean Adrien Cassel and Thierry Lévy and other people have been doing closer related things. Imagine you are in dimension 3, and you put an axis, but of course you can generalize it, right, like that. And you see a sandpile, and you see that the sandpile, contains a non-trivial loop around this axis. Okay, when I say it contains a non-trivial loop, the place where this thing is strictly positive has, non-trivial topology with respect to that thing. You could do that in dimension d, and you put a d minus 2 dimensional tube, and you look at, some structure. So now we're going in directions that are reminiscent of twisted GFF type things. So you imagine that you see that this island, makes a loop around this. Now the question is, what can you say about the individual Brownian, what's the law of this collection, of the collection of sandpile when you condition it to have a non-trivial, contain a non-trivial loop here? And the variant of that result that we were writing up with Titus is, in some sense, it's just a normal Brownian loop soup. But then you condition, okay, you have to be careful how you say it, but sort of this, you can condition it on having an odd number of actual Brownian excursion, Brownian loops that go around. So one other version would be, if I look at the picture and I say, okay, I see that this thing goes around, it has an island that goes around. What's the number of loops that actually make it inside, Brownian loops that do the job? Their number will have a conditional probability 1/2 to be even and 1/2 to be odd. These type of results, right? So you can sort of decompose in the same way that these objects conditioned on these 2 points, you can condition on non-trivial, non-trivial things, and you get results like that. So one outcome, so this is sort of not unrelated to, loop decorated, or how you call it, loop rooted, how did you call this? Cycle rooted forests. Yeah, it's not unrelated to that. And so let me just explain you, if you're in dimension d equal to 7 or higher, one result, which sort of resolves an open question by Titus. So when you are in high dimensions, then you're in this world where, physicists will say it's trivial, right? It's a triviality of the field. So, all these islands will typically be tree-like structures because the dimension is so big, and you'll have plenty of them. You have proliferation of islands. You don't have proper scaling limit. However, you can imagine that you have a d minus 2 dimensional tube, and then you look at, you condition on the fact that in this very high dimensional space, there is a cluster that wraps around some given tube. The outcome is that in the scaling limit, when you let the mesh go to 0, you have a probability exactly 1/2 that this loop is actually one Brownian loop in your loop soup that happened to be there, and then you attach, then you have the cluster attached to it will be all these trees. The conditional probability is 1/2 once you have the picture. And the other 1/2 contribution will come from that this big loop has been created by a chain of loops that are each of them microscopic at the level of the picture. So that, and you can't distinguish between these two scenarios because it could be either one or the other, and it's 1/2, 1/2. So we have a paper with Amelia Carpenter that we're going to post soon, which says, oh, actually, this tells us we can do something very simple as well for ordinary percolation in ZD, which gives rise to the fact that, well, Eisenman and all the others says, everything's trivial, nothing happens in these high dimensional structures. If you look at the clusters, because you're looking at the, pointwise correlation function, and then it tells you, okay, typically a cluster is looking like a tree. But if you look at the clusters that don't look like trees and you condition them to have loops, well, then these loops will be distributed in the scaling limit like a Brownian loop soup. And there's a non-trivial scaling limit. They don't proliferate. So you have this sort of thing that, you know, in retrospect says, oh, okay, you know, now, of course this, you know, if you tell that to anybody working in high-dimensional percolation theory, said, oh, you know, if you tell me that, I'll know how to prove that indeed you have these loop soups showing up in the scaling limit in high dimensions, but that's sort of, you know, also something you can do. So in some sense, even in higher dimensions, where we are usually told nothing interesting happens because, you know, clusters all look like tree and, well, no, if you look at those that have non-trivial, non-trivial topological structures, actually at macroscopic level, actually there are scaling limits and they are non-trivial. Well, they're not that interesting either because you could say, well, they are like Brownian loops, but you can also, you know, have some other, you know, and you know, you could look at clusters, you know, that have features like that, where they have almost loops that touch twice, and those will also give rise to scaling limits. So you can, you know, there's a whole zoo of interesting things that happen in high dimension there as well. Yeah, and I think I'm out of time, so I know that I wanted to say other things, but don't pop in my head right now, so I think I should probably stop here. Thank you.
Okay, thank you. So any questions from the audience, and please wait for the mic.
I was going to ask, to what extent does this story depend on the parameter C? And then I was going to ask, to what extent does it depend on the dimension of the lattice? But maybe a better question is, to what extent does this story just depend on the graph? Is it?
It doesn't. It works for any graph, basically.
Right.
So it does depend on dimension D. This is like something that happens everywhere. That's also, you know, then you can try to, you know, put in holonomies or whatever, and then you try to see what happens. It crucially depends on C equal 1. Because C equal 1 is the one where basically when you do your rewiring, because C equal 1, you don't care about the number of loops. In the other cases, you would have to, you know, do some sort of a rewiring procedure. So it is everything that works for this particular magical intensity C, which is related to the Gaussian free field in an intrinsic way, and the proofs are, you know, use this Gaussian free field Markov property in various ways. Yeah. I should add one thing that, you know, in the case, Elie Idecon, you know, after I posted the paper, he sent me this thing, you know, because I wrote this comment. I said, obviously, this is the type of, you know, if you look at this in the case of that graph, it's not a very difficult graph, it's just one edge. And you look at it and you say, well, then it has it's a relation that tells you that I conditional, you know, the square of Brownian motion to do not hit 0 on the interval, and it has the law as the squared Bessel of dimension 1 plus 4k, where k is a randomly chosen something it looks like. And I thought, okay, if it's true, then Mark Yor, for those who knew, Mark Yor would have proved it. And I wrote that, and then Elie sent me the email, said, yeah, he did. You know? So actually the version in that thing is in one of the famous Pittman-Yor papers that, again, for those of you who weren't born in those days, you know, Pittman and Yor, you know, they went on holiday hiding in an office somewhere and writing 3 or 3 papers each summer. And one of these papers was exactly, you know, oh, we have this strange identity in distribution, but we have no idea, you know, this looks very bizarre, but yeah. So in some sense, you know, Mark Yor, although, you know, he knew how to compute Laplace transforms of lots of functionals of Brownian motion, you know. And of course, if you know that, okay, Laplace transform is something with Poisson point processes, right? E to the minus something is just a probability that this thing doesn't happen, and then he was doing loop soups, but he didn't know it yet. Yeah.
Any other questions?
Is there an oriented analog for the other value of C?
Okay, so that's a very good question. That's the other thing that has been bugging me for many years. You know, in some sense, the answer to you know, this identity, in some sense, it was always this problem that, you know, the Gaussian free field has the Markov property, the loop soup has the Markov property, and somehow it doesn't really fit because you have this even odd thing. So, you know, if you see, you know, so let's put it this way, if you cut a line in the middle, and you see that on the right-hand side the Brownian loops do that, and there's this giant excursion going from here to there, then you want to say, well, probably on the other side, this one has to come back. So, you know, there ought to be a big one on the other side as well. And therefore, they're not as independent as they should be, you know, these type of things. And so this type of thing just says, yeah, it doesn't matter, because, you know, if you have this one, you might as well come back, you know, creep your way through the small stuff anyway, and therefore you are going to, so there is this sort of a, you know, you can say, you know, now I get it why, you know, why it works and why is this identity actually, you know, you have these two Markov properties of the square of the Gaussian free field and of the Gaussian free field itself, and you can sort of work out around it. Now, if you take C equal 2 and you take the oriented one, you have a similar rewiring property. And then you get into a realm of there ought to be some important field around. And once we put our finger on it, we'll be able to say, yeah, okay, you know, now permanent, blah, 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 you know, these different things that as probabilists we understand, can follow the proofs, but we don't have the, you know, actual, you know, intuition about, you know, enough intuition about it. There should be this other field around that. With my former student Mattis Limkula, we did spend many hours in front of the blackboard, and made my previous students as well trying. So there are lots of ideas one can make. So, but there is going to be some field which is not Gaussian, not completely unrelated to the Sine-Gordon stories that we heard yesterday, which has to do with, you know, some random fluxes. Where, but again, you know, if you have these oriented edges, then this even odd thing maybe cannot be dispensed with, because, you know, the orientation is sort of more rigid structure, and so it's not clear that there will be, you know, this magic here will work for that other type of field. So I don't think so. Yeah. It might be that something similar happens with, you know, people doing, you know, double current, and okay, well, you are well placed to know that because you discussed with Martin and Dima and so on. They, you know, you will know that, you know, you have these things where, you know, you have you can put two sources, you know, you could take two independent copies like that, and then there are two odd things, and then the two odd things become even, and then you can, you know, recover the other one, find the other loop. It is very much reminiscent of this, you know, these general rings bells in that direction, but it's intrinsically different, I think, because of this. You need to be on this continuum world in order to, you know, have this switching bijection. Oh yeah, the final thing I want to say, they call it a switching identity because it sort of says that there is a natural combinatorial way, right? The fact that the even condition to be connected and odd things have the same distribution in terms of the accumulated sandpile tells you that there's a bijective way to go from one to the other. And you sort of, and there's a way to make sense of this bijective, you know, replumbing, rewiring. But of course, if you want to, you know, change even to odd, you know, you connect this one to come back then, but then you break another loop, and then you have to, you know, so you have to, your plumbing thing is like you go from the macroscopic in order to change this macroscopic number of things, and then you have this, you know, cascade of smaller and smaller fixes you need to put at the, you know, all the way down. But that's a way to do. And to go in that direction, it's very useful to use this approach that some of you have heard by vertex reinforced jump processes, you know, this sort of reinforced random walk type thing developed by Christophe Sabot, Pierre Tarès, and Joel. Yeah, so there is a, you know, yeah, as I said, it goes in quite a number of directions, so I should say.
Right, so let's thank the speaker again.
Yeah.